A single person could move a 20-ton stone door with one hand. That's not a myth. It's ancient engineering. There's a hidden mechanical genius in those old doors. Principles modern engineers still look at. You start to see history as a living source of solutions. Solutions to problems we still have. How did a civilization without steel make doors that sealed tombs for thousands of years? What secret counterweights let guards lift gates heavier than elephants? The answers are out there. From Egyptian temples to medieval castles. To build something that lasts, for what does that take? Those huge stone doors. They didn't swing on hinges. They turned on a single point. A carved knob at the bottom of the door fitting into a hollow socket in the floor. Another one at the top fitting into the stone above. That created a vertical axis. The whole weight of the door, maybe 20 tons of solid rock, was now resting on these two small, hard points. It seems like it shouldn't work. That much pressure should just crush the stone. But that's where their understanding shows. By concentrating the load onto a tiny area, they actually reduce the friction. It's like the difference between sliding a crate across the floor and tilting it onto a corner to spin it. The pivot became a kind of bearing, a primitive one but effective. Roman engineers, Vitruvius wrote about using bronze for these pivots, a harder material to resist wear, so the idea evolved. This principle, reducing contact to ease movement, you see it now, in a revolving door, in the bearings inside a car wheel. They mastered a basic law of physics with stone and geometry. To move a mountain, you don't push the whole mountain. You find the one point where it can turn. That pivot solved one problem, but then there was a bigger one. How do you lift a gate that weighs as much as a house? The answer was to not fight the weight. You make the weight work for you. High up in the gatehouse, inside the stonework, there was a secret chamber. And in that chamber was a massive wooden box, or maybe a lead block. It was connected by a thick rope or a chain that ran over a pulley and down to the top of the gate itself. That was the counterweight. So when the guards needed to raise the portcullis, they weren't lifting the iron lattice. They were just releasing a brake, and the heavy box in the chamber above would start to fall. As it fell, it pulled the rope, and the rope lifted the gate. The human effort changed. It went from brute force to guiding a balanced system. It became about overcoming inertia and friction, not dead weight. That was the leap. It meant understanding that the force you need isn't about the object's mass alone. It's about the system you build around it. And this principle was ancient. Centuries before these castle gates, farmers along the Nile used a simple tool called a shaduff for irrigation. A long pole was balanced on a crossbeam. A bucket on one end, a heavy lump of clay or stone on the other. A farmer could pull the bucket down into the river, fill it, and then the counterweight would help swing the full bucket up. The same core idea, scaled from watering a field to securing a fortress. That insight that you can engineer balance into existence, it's a direct ancestor to our world. Look at a bascule bridge, the kind that tilts up. The entire massive roadway is balanced by a hidden counterweight below. That's what makes it move smoothly. Every elevator you ride in operates on this same ancient trust in counterbalance. The engineers of the past looked at a massive door and asked a different question. Why lift it when you can balance it? This mastery of static forces, creating equilibrium where none existed, it shows a mind thinking in systems. But it leads to another question, a more intimate one. Once you have this perfectly balanced door, moving with a gentle push, how do you make sure that when it closes, it stays closed? How do you seal the gap between moving stone and stationary wall? Not just for a day, for 1,000 years, that perfect balance lets the door move easily, but it leaves a gap. And a gap is a problem. It lets in drafts, dust, things you don't want. For a tomb door, that gap meant a failure, a sacred purpose broken. So the builders focused on the place where the door meets the ground. They didn't just use a flat stone. They engineered the threshold. Think about the bottom of a big bronze door or a wooden one. If it just dragged across a flat floor, it would bind, it would scrape. It would wear itself down until it was useless. The solution was elegant. They set a raised stone sill into the doorway. And into the top of that sill they carved a channel, a precise groove. That groove acted as a track. The lower edge of the door would sit down inside it. So when the door swung, the groove guided it. It stopped the door from shifting sideways. It kept it from wobbling out of alignment. A simple containment system. At Persepolis you can still see these grooves, worn deep into the stone by centuries of doors moving back and forth. A silent record of daily life, of a design that endured. This is one of the earliest forms of linear guidance, the ancient ancestor of a drawer slide. Or the rail that guides a machine tool. It's the same principle. Restrict movement to one path, reduce the friction, reduce the wear. But a guiding track only solves part of it. A door has to seal too, and for that the threshold design got more sophisticated. Sometimes that channel would be lined with lead or bronze, a softer metal. It would conform to the door's edge, create a seal against the weather. In other designs, the threshold itself was shaped to interlock. A raised ridge on the sill would fit into a slot on the door, like a puzzle piece clicking into place. That did more than stop drafts, it added rigidity. It meant the door, when closed, became part of the wall. That strip of stone at your feet was never just a step, it was a bearing surface, a wear component, a seal, the foundation of the entire door's mechanical function. Modern engineers look at these thresholds with respect. They see the fundamental problems: alignment, load distribution. Material wear, problems they still solve today. The challenge is timeless, making two large surfaces move against each other smoothly, then lock together securely. From those stone grooves, a line runs to the sealed hatch of a spacecraft, to the massive floodgate of a dam. The ancients understood. A door isn't just a barrier, it's a moving joint in the building's skeleton. And every joint needs a carefully designed point of contact. A perfect seal goes beyond just being tight, it's a barrier. For Rome, protecting grain was survival. Their granaries held food for entire cities. A leaky door wasn't an inconvenience. It meant spoiled grain, hungry people, unrest, so they engineered a solution. They didn't just build a thick door, they carved the door and frame with interlocking steps, a rebated edge. When it shut, these steps nested together. They created a long, winding path. Air couldn't rush straight through. Moisture couldn't seep in easily. It was a labyrinth. This wasn't just woodworking. It was early environmental control, managing the microclimate inside, using geometry to defeat humidity. You see a similar principle today. Freezer doors, spaceship hatches, creating a tortuous path that air and water can't follow. Then there were the Egyptians, facing a different eternity. For a tomb door, the enemy wasn't just damp air. It was the desert itself, dust, sand, particles that could fill a sacred space over centuries. Their solution was adaptive. Evidence suggests layers of fabric, maybe linen, packed around a stone door's edges, then covered with wet plaster or clay. As it dried in the desert heat, it would shrink and harden. But here's the clever part. If moisture ever found that seal, the material would expand again, tightening the closure, a self-adjusting gasket, a seal that responded to its environment. This shows a deep understanding of material behavior. They weren't just using stuff. They were anticipating how it would change over time, under different conditions. They engineered for the long term. Modern engineers see the roots of their own work in these methods. That Roman rebated door is an ancestor of the seal on a submarine hatch. Keeping water out is life and death. The pressure differential is immense. The seal has to be perfect. It uses the same principle, a complex interlocking path that becomes stronger as outside pressure increases, wedging it. The Egyptian expanding plaster finds an echo in aerospace polymers, O-rings and gaskets that must seal under wild temperature swings. From the freezing cold of space to the searing heat of re-entry, these aren't just better materials. They're the same ancient puzzle, solved with new tools. How do you join two things so completely that nothing else can get between them? The drive for a perfect seal reveals a fundamental desire to create a defined space, to keep the outside out and the inside in, whether it's grain, a king's remains, or the air in a spacecraft cabin. This mastery over the boundary leads to the final expression of ancient door technology, the seamless joint. If you can make a door seal perfectly, could you make the very walls around it disappear? That seamless joint where the door just becomes the wall. It shows you something. The most secure door isn't something you fit into an opening. It is the opening. You have to look at the walls to see it. The walls at Mycenaean. These huge limestone blocks, some weigh over 20 tons, stacked into fortifications so big the Greeks who came later thought only giants could have built them. They're dry stone walls, no mortar, no cement, just these colossal, irregular stones, each one shaped uniquely, fitted against its neighbors with a terrifying precision. The joints are so tight you can't slide a knife blade between them. That's the art of interlock. And the doorways in these walls were built with the same logic. The jambs, the vertical stones framing the door, and the lintel across the top. They were often single monolithic blocks. Into these stones the builders carved precise sockets and tenons. It's a giant stone puzzle. A protruding knob on one block fits perfectly into a hollowed-out recess on another. Then gravity does the rest. The immense weight of the wall above presses down. It locks these joints together. The doorway wasn't a hole cut into a finished wall. It was a key component woven into the wall's fabric. Each interlocking joint transferred the structural load, distributed the crushing weight of the mountain of stone above. The doorway itself became a load-bearing element, a masterpiece of compressive force. Modern structural engineers study these walls, not as ruins but as textbooks. They see a profound understanding of passive stability. The absence of mortar wasn't a limitation, it was the genius. Mortar is rigid. When the ground shakes or the structure settles, rigid materials crack, they fail. But a dry stone wall with its intricate interlocking joints can flex, it can shift, it can settle without collapsing. The stones move as one, friction and gravity holding them. This is an ancient lesson in designing for dynamic loads, for earthquakes. It's a principle you see today in certain seismic-resistant masonry, where flexibility is engineered into the structure to absorb energy. This macro-scale joinery, this stone puzzle on a colossal level, it required a mind that could think in 3 dimensions and across vast scales. It foreshadowed the precision that would be needed on a much smaller stage, more intricate, because a door that is part of the wall still needs one final piece. It needs to be secured. And to lock a door built with such monumental care, you would need a device of equal ingenuity. A mechanism that could take the principle of the interlocking stone, security through precise fit and miniaturize it, into an elegant movable secret. That stone wall needed a lock that could think. Security isn't just about strength, it's about who controls the barrier. So picture an ancient Greek home. The door is shut. To lock it, someone inside slides a heavy wooden bar across the back. This bar, the diabetes, falls into a slot in the stone frame. It's a simple move. But then how do you leave? You've locked yourself in. The answer was a hole drilled through the door. A leather thong was tied to that sliding bar inside. The other end was fed out through the hole. To leave, you'd pull the thong from outside, sliding the bar back, opening the door. To lock it behind you, you'd push the thong back through the hole, letting the bar drop into place by its own weight. It's a deadbolt, one of the very first. The genius is the remote operation. A simple cord translates a pull outside into a slide inside. The principle is mechanical linkage. It separates the action from the effect. We do this every time we use a key. The turn of your wrist in the lock cylinder becomes the slide of a bolt you never see. The Greeks had miniaturized the counterweight. They used gravity and friction to create a reliable state, locked or unlocked with one simple input. But what if you needed to let someone else in? You couldn't leave a leather thong hanging outside. That needed a new layer of complexity. In Egypt about 4,000 years ago, they made a mechanism that feels familiar. A large wooden bolt was fastened to the inside of a door. On the bolt there were vertical holes. Above it in a wooden housing rested several wooden pins. When the bolt was pushed closed, these pins would drop down, driven by gravity into the holes. They pinned the bolt in place. It was immobilized. To open it, you needed a key. But this key wasn't a metal twist. It was a long wooden stick with pegs sticking out in a specific pattern. You'd insert this key into a slot beneath the bolt and lift it up. The pegs on the key would align with and lift the specific pins out of their holes just high enough. With the pins disengaged, you could then slide the bolt back. This is the pin tumbler lock, the direct mechanical ancestor of the lock on your front door. The security didn't come from the strength of the wood. It came from the secret pattern, the specific arrangement of pins that only one unique key could match. It was a puzzle of elevation. The Egyptians had invented a security system based on information. The key wasn't a tool of force. It was a carrier of a code. Modern engineers don't study these locks to improve home security. They look at them as elegant studies in basic physics. Gravity provides the force that engages the pins. Friction must be overcome to slide the bolt. Pins create a shear line, the plane where the bolt can move only if the pins are perfectly aligned. These are the fundamental forces that every lock, no matter how advanced, must still master. The modern electronic lock still has a bolt that slides. It still must overcome friction. It just uses a motor instead of a hand. The biometric scanner still has to align the pins, so to speak, by matching your fingerprint to stored data before it releases the shear line. The core logic is unchanged. A sequence of simple, reliable mechanical actions arranged to create a binary condition. Secure or not secure. This progression from the leather thong to the wooden pin lock shows a civilization moving from securing a space for convenience to securing it for controlled access. It's the birth of the key as a personal token, an object that carries permission. That concept would eventually be scaled up dramatically, because the next challenge wasn't about keeping a single person out of a house. It was about managing the flow of an entire population through a sacred, monumental space. How do you design a door for a crowd, for a ceremony, for an event that is itself a performance? The locking mechanism had to become part of the spectacle. A lock is private. It's a secret between the mechanism and the key. But then you have a door meant to open for a public audience. When the act itself is a sacred spectacle, that's the final principle. It shifts from security to symbolism. From the hidden pin tumbler to the grand, theatrical reveal. Ceremonial kinetics. Engineering harnessed not just to move mass, but to move hearts and minds. Think of the inner sanctum of a great temple, the most sacred space. That door wasn't merely an entrance. It was a veil between the human world and the divine. Its opening couldn't be abrupt. It had to be an event. A slow, majestic parting, a deliberate revelation. So how do you engineer reverence? Some accounts describe hidden counterweights, filled with sand or water. A small, calibrated hole would let the sand trickle out, or the water slowly drain. That would regulate the descent of the weight, and the weight would pull a rope or turn a drum, drawing the massive doors open at a precise, unhurried pace. The speed was the message. It created anticipation. It transformed a physical action into a timed ritual. The most famous stories come from Hero of Alexandria, a first-century engineer. He described automatic temple doors. His design was a masterpiece of theater. He proposed an altar fire. The heat from the fire would cause air in a sealed vessel to expand. That expanding air would push water through a siphon, into a bucket. As the bucket grew heavier, it would descend, pulling ropes that turned axles, and those axles, through gears, would swing the great doors open. No human hand touched them. It would have seemed like magic, a divine response. The doors moving by the will of the god. Historians debate how often such systems were built, but the principles Hero described are sound: thermal expansion, hydraulic pressure, gear reduction. He was blending physics with performance. He understood mechanics could create wonder. Modern mechatronics engineers look at Hero's accounts as a conceptual leap. They see in that altar fire an early sensor, a heat source triggering a chain of events. They see in the gear train a primitive program, a fixed sequence. The bucket filling with water is a timer. The whole system is a one-act play written in physics. This is the seed of automation, a machine performing a complex timed sequence from an environmental cue. We see its legacy everywhere, in automatic sliding doors triggered by a motion sensor, in the sequenced lighting of a stage show, in the programmed movements of an assembly line robot. The goal is the same: a reliable, repeatable, often dramatic kinetic event. That fusion of function and spectacle is a reminder. Ancient engineering served awe as much as utility. A door could be a statement, part of the architectural story. The slow swing of a temple door wasn't just about getting from one room to another. It was about controlling emotion, marking a transition from the profane to the profound. It asked the audience to pause, to watch, to feel the weight of the moment. In that deliberate motion, you see the ancient understanding. Technology is never neutral. It shapes experience. It can humble you or fill you with reverence. The door becomes more than a barrier. It becomes a performer in the ritual of the space. This final principle connects the distant past to our present, because we still design for this effect. The gentle, silent close of a luxury car door, the satisfying click of a well-made safe, the sweeping, automated theater curtain. These are all engineered sensations, ceremonial kinetics in everyday life. They prove advanced engineering often seeks to replicate that ancient magic, not just to solve a problem, but to create an experience. One that feels in its perfect motion almost sacred. A door could be an instrument. It had a hidden property beyond just moving: its voice. The sound it made when it closed. In a deep, silent tomb, a huge bronze door wouldn't just shut, it would resonate. The builders knew this. They picked the metal, decided how thick it should be, how to mount it, not just for security, but for the sound. A deep, solemn tone was part of the design. That resonant frequency wasn't an accident. It was engineered to make you feel something specific: reverence, or awe, maybe a little fear if you were standing there. It's a profound layer of ancient material science. They were manipulating sound through form and substance. Modern acoustic engineers look at these artifacts. They see in the alloy an early grasp of sound damping. Different mixes of copper and tin made bronze with different densities, different internal structures, and that changed how it vibrated. how it absorbed sound or reflected it. The mounting method was just as critical. A door bolted rigidly to stone would transmit vibrations one way, a door on pivots with a small gap would do it another. The ancients learned to control these things, through trial, through observation. They were shaping the auditory experience of a space, as deliberately as the visual one. This goes beyond metal. Think of the big wooden doors in a cathedral or an ancient theater. The type of wood, the grain, the bracing pattern on the back, all of it influenced the sound. A thick oak door might muffle noise, create a hushed interior. A lighter door in a theater might be tuned, to avoid vibrations that would clash with the music. The door became part of the acoustic shell, a component in a system made for listening. It shows a holistic way of thinking, one we sometimes miss. An ancient door was rarely just one thing. It was a barrier, a bearing, a lock, a theatrical device. And an instrument? Its design needed a deep, intuitive understanding of material harmonics, how a substance behaves not just under weight but under vibration. They listened to their materials. They understood bronze could sing, that wood could whisper. This acoustic awareness points to a broader truth about how these civilizations used the stuff of their world. It suggests their material choices were often symphonic, considering properties far beyond strength, which makes you wonder. If they could engineer the sound of a door closing, what other sensory experiences were built into the stones? The answer is in the walls. In a principle so subtle, most of us walk right past it. The sound of a door came from what it was made of, and that choice usually pointed to a deeper idea. A door wasn't one thing. It was many things put together. That's composite construction. Take a Roman city gate. It was its own defensive system, not just iron, not just oak. It was built in layers. They started with a heavy timber frame. They fitted thick oak planks into that frame. Then they bound it with a skeleton of iron bars. And finally they covered the whole outside with sheets of hammered bronze. Each material had a role. The iron gave tensile strength. It held everything together, kept it from pulling apart. The dense oak was for absorbing shock. When a battering ram hit, the wood would compress. It would deform. It dissipated the energy. It wouldn't just shatter. And the bronze was the skin. It resisted corrosion from weather. It presented a smooth, hard face that was hard to set on fire, and it could be polished. A gate that gleamed in the sun was a statement, power and permanence. This layered method solved many problems at once: penetration, fire, rot, structural fatigue. The builders knew no single material was perfect for everything, but by combining them, they made something greater than the parts. Modern materials scientists see these old composites and they recognize the thinking. It's an early form of laminate theory, bonding layers with different properties to create a superior material. The oak was the compliant layer for absorbing. The bronze was the hard face for deflecting force. The iron was the reinforcement, holding it all under tension. That synergy is the basis of modern composites. A bulletproof panel works the same way. A hard ceramic face shatters the projectile. Then a fibrous backing like Kevlar catches the fragments and absorbs the leftover energy. An aircraft fuselage is a complex laminate. Aluminum alloys, titanium, carbon fiber, each chosen for a specific property, lightness here, strength there, heat resistance somewhere else. The ancient gate builder was thinking the same way, just with the materials he had. He wasn't just building a barrier, he was engineering a response to a list of threats. This holistic approach shows a mindset. The door wasn't an object, it was a system. Every layer, from the bronze skin to the iron bones inside, was part of an integrated defense, technology from necessity, resilience through combination. It shows that the most enduring solutions don't come from one perfect answer. They come from weaving several good ones into something new. That gate was a system, but it was part of a larger trap. The strongest door was never meant to stand alone. It was part of a deadly geometry. The entrance to a castle under siege was never a straight line. It was a puzzle. You'd come to the outer gate and the passage behind it would bend. Turn sharply left or right. That's the bent entrance, the chicane. Its purpose was brutal. It broke the momentum of a charge. A battering ram crew couldn't get a running start. They'd have to shuffle around a corner exposed. And the door at the end wasn't facing them. It was set back in a recess or angled, so the ram's swing was awkward, glancing. The door became a surface. Those iron bands weren't just decoration. They were reinforcement. Ribs in diagonal or radial patterns. They weren't just strong. They were shaped to guide a blow, to slide the force away from the lock, the hinges, the weak points. The studs on the face weren't random. They created a textured surface. It could catch a ram's head, splinter it, spread the energy out. This was defensive geometry. Every angle, every surface calculated to redirect force. To turn a direct hit into a glancing one, military architects study these layouts. They see them as early in passive defense. You see the same idea in a modern tank's sloped armor. Angling the plate doesn't just make it thicker, it makes a shell more likely to deflect, to skid off. A bunker's entrance is never a straight corridor for the same reason. It's a zigzag, a chicane. So any explosive blast loses its focused power around the corners. The ancient gate builder understood this. He wasn't just building a strong door, he was designing a force field. By angling the approach and shaping the door's face, he engineered the attack. He dictated where the energy would go. That's a profound shift, from pure resistance to intelligent redirection. It shows a mind that saw defense as a conversation, an action and a calculated reaction. The door was a component in a larger kill zone. Its mechanics were part of the castle's whole strategy. The pivot let it swing shut fast. The lock held it firm, but the angle of its face and the path to reach it decided if an attack would ever land clean. This was systems thinking. It considered long-term durability in a relentless environment. A door that only resisted would eventually fail. A door that deflected, that made attacks inefficient, could endure 100 assaults. It's a lesson in designing for abuse, not to prevent it but to manage its effects. To make the system survive not through immovable strength but through clever geometry. That ancient logic of deflection finds its way into our most advanced protective designs. But it also points to another kind of ancient genius, a quieter one, not about stopping armies but about mastering the silent, relentless forces of the earth itself. Because the greatest threat to a monumental door was often not a man with a ram. It was the ground slowly shifting beneath it. The ground under a fortress is always moving, settling, shifting with the seasons. A door that weighs 20 tons swinging back and forth for 100 years will wear its own home down. That pivot socket in the floor, that stone cup holding all the weight, it grinds deeper. A millimeter each year. Over a century, that's a finger's width. Enough for the door to sag, to stick, to stop working. But the builders knew this. They weren't designing for the day it was built. They were designing for time. That's where compensation. They expected that slow grind. In some designs, that pivot stone wasn't part of the main threshold. It was a separate block, a plug, carved to fit into a socket in the bigger foundation stone. When it wore down too far, you could pry it out and put in a new one, a fresh surface, without tearing the whole doorway apart. It was a modular piece. A spare part built in from the start. Other designs allowed for adjustment. The metal straps holding a huge wooden door to its pivots might have a line of holes. As the wood shrank or the hinges wore, you could move the mounting point. Retension everything. It's a simple idea, but it means something. It means the structure is alive. It changes. So the design has to allow for that change. You see this same thinking in ancient shipyard gates. Big wooden doors that held back water for repairs. The leading edge, the part that sealed against the sill, it got scraped by silt and debris constantly. So the builders set strips of a harder wood into that edge. When those strips wore thin, you could pry them out and slot in new ones, a sacrificial piece. The main gate could last generations because its weakest part was made to be replaced. Modern engineers see these solutions and recognize them. This is where the bushing comes from, the bearing, the wear plate. In a car engine, cylinder liners can be replaced when they're worn. The piston rings are sacrificial. They wear down so the cylinder walls don't have to. On a mining excavator, the bucket teeth are bolted on. They're meant to be ground away and swapped to protect the bucket itself. That principle, designing for specific parts to wear out in a planned way, it's basic to all machinery. It's maintenance built right into the blueprint. It's a shift from seeing a door as a finished monument to seeing it as a system with a life. The best engineering isn't about stopping all wear. It's about managing it, directing it, deciding exactly what will wear out, how easy it is to fix, and how the whole system lives with that process. That foresight to design for slow erosion, it shows a mature conversation with the natural world. It accepts that entropy is a partner in the design, not just an enemy. That mindset prepared them for a more violent partner, because the earth doesn't just settle quietly. Sometimes it shakes. And the real test for an ancient door wasn't a siege. It was an earthquake. The earth shaking was the ultimate test. No amount of wear compensation could fully anticipate that force. For a door to survive, it needed a different kind of resilience. It needed to be part of a structure that could sway and then settle back. But there were other forces, more deliberate ones that ancient engineers also learned to command, not with stone and gravity but with water and air. The accounts are rare. They're more like thought experiments. Hero of Alexandria, that same first-century engineer who wrote about the theatrical temple doors, described a system powered by an altar fire. His design was a chain of physical poetry. The heat from the sacred flame would cause air inside a sealed bronze vessel to expand. That expanding air would push against a column of water, forcing it through a narrow siphon. The water would flow into a bucket. As the bucket grew heavier, it would descend. Its descent would pull ropes wound around a drum, and that drum, through a series of gears, would slowly turn the axles of the great doors. They would swing open, seemingly by divine will, without a single person touching them. The principles at play were profound, even if such a device was more a model of understanding than a common fixture. Thermal expansion, heat makes air push outward. Fluid displacement, a pressurized gas moving a liquid. Pascal's law, though not yet named, whispering in the background. Pressure applied to a confined fluid is transmitted equally in all directions. Hero was sketching a blueprint for a primitive heat engine. A machine that converted thermal energy into mechanical work through water and air. Modern hydraulic and pneumatic engineers look at these ancient concepts not as practical blueprints, but as brilliant flashes of insight. They see the seed of the piston and cylinder in that heated vessel and displaced water. The entire idea of using a confined fluid to transmit force and control motion is right there. It was a leap from using human or animal muscle, or even counterweights, to harnessing an environmental energy source. The fire itself became the actuator. What's most compelling is the shift in focus this represents. It moves beyond raw power to the precise control of movement. The siphon, the bucket, the gear train, they were all regulators. They took a burst of thermal energy and transformed it into a slow, majestic, and repeatable motion. The goal wasn't just to open the door. It was to orchestrate the speed and the spectacle of its opening. This was engineering as ritual programming. Widespread archaeological evidence for such hydraulic doors is scant, but the principle of water power was certainly known. The Romans used water wheels to grind grain. The concept of using water's weight and flow to turn things was ancient. So the idea of channeling that force to operate a gate or a door wasn't a huge conceptual leap. It was an application of a known power source to a new theatrical purpose. This exploration of alternative power, fire, water, air, reveals an ancient intellectual bravery. It shows a culture willing to play with the fundamental levers of physics, to combine them in novel ways to create wonder and automate sacred rituals. They were beginning to see doors not just as barriers or passages, but as kinetic sculptures, as the final moving piece in an environmental machine. This drive to automate, to remove the human hand from the direct act, points toward a future where machines would not just assist us but perform for us. It completes a journey from the sheer mass of a stone pivot to the ethereal control of heated air, and it leaves a final, unifying question. After seeing all these principles, from balance to acoustics, from composite layers to hydraulic dreams, what does it all add up to? What is the single, overarching lesson these ancient doors still teach the engineers of today? The wedge was the last step. That final, gentle lift. It's a simple shape, one of the oldest tools. When a stone door was almost closed, but the bottom was dragging, they had a solution. They'd take a wooden wedge or bronze, place the thin edge under the door's lip, then a hammer tap. That small force on the wedge's wide back created an immense sideways push. It lifted thousands of pounds, just enough. A micro-adjustment, an act of alignment using the inclined plane. Think of the wedge as a moving ramp, a ramp you push under something. The longer and thinner it is, the greater the advantage. A small force over the long slope becomes a huge force over a short distance. That's what lifted the door. The builders understood this trade, force for distance. You swing the hammer a long way to move the stone a tiny, precise amount. This wasn't just for doors, it was fundamental. They use wooden wedges, soak them with water, drive them into granite cracks. The wood would swell and the wedging force split the stone clean. To raise an obelisk, they'd build a sand ramp, drag the stone up, then let the sand pour out from a hole, lowering it vertical. The ramp is a stationary inclined plane. The wedge is its portable cousin. Modern engineers study the wedge as pure mechanical advantage, a direct application of physics. No moving parts, just geometry and force. You see it in a log splitter, in a sculptor's chisel, in a tapered shim that levels a washing machine. The principle is identical: concentrate a diffuse force into a precise, powerful line. For the ancient door, the wedge completed the system. The pivot was the bearing. The counterweight provided the lift, but the wedge delivered the final control, the precision tool in a macro-scale operation. This shows their engineering mindset. They didn't see simple machines as separate ideas. The lever, the pivot, the inclined plane, they combined them. The door itself, swinging on a pivot, was a lever. Its counterweight was a lever system. The wedge was the inclined plane that fine-tuned it all, combinatorial ingenuity, building complexity from a few perfect, interoperable parts. That same thinking, that combination of principles, didn't stop at making doors work. It extended to making them speak. Because once you have a door that moves with perfect balance, you might want to announce its presence. Not with a creak, with something more deliberate, something that turns mechanics into music. The iron vines on a cathedral door. They're not just decoration, they're a story of strength. If you look, the metal tendrils all swirl toward a central point, a domed boss. It's beautiful. But it's hiding something. Under that bronze rose is the head of a massive iron rivet, a bolt that goes straight through the oak planks. It binds them together from the outside. The ornament is a disguise. It turns a structural necessity into a feature. Ornament as reinforcement. The principle is elegant, beauty with a purpose. Those iron straps, the strapwork, they do more than show leaves and flower. They act as a tension ring. Wood on that scale wants to move. It swells with humidity, shrinks with dryness. Over centuries, that movement can cause splits. But the iron bands, forged and fitted when the wood was seasoned, they hold it. A constant, gentle embrace. They prevent warping. They distribute stress. The most delicate-looking tendril is a load-bearing element, placed right where a joint or a panel edge was prone to fail. Modern designers study this fusion. They see how do you hold something together, and how do you make that method beautiful? It challenges the idea that form and function are separate. For the medieval metalworker, it was one conversation. You see this thinking everywhere now, even if we miss it. The sleek aluminum shell of a laptop. That's not just for looks, it's a unibody. The outer casing is the structural frame, it's rigid, it protects, and its form is its function. A speaker grill, it's not just a pattern, it's a calculated mesh. It protects the driver and lets sound pass through. The curved glass on a smartphone, more than a beautiful surface, it's a structural element, chemically strengthened to be part of the armor. The old door makers understood stress. They knew a sharp corner in metal was a point where force would gather, a potential tear, so they rounded everything. They turned functional transitions into flowing curves, into floral motifs. They hid the hard points of engineering inside a language of natural beauty. This philosophy went beyond the metal, into the wood itself, the grand symbols carved into the panels, figures of saints, scenes from scripture, more than decoration. On a practical level, carving away some of the wood's surface could relieve internal stresses, prevent random cracks, but on a deeper level, it integrated the door's purpose into its physical being. The door wasn't just an entry to a sacred space. Its surface told the story of what was inside. The art was the introduction. The function, security, durability was the unseen foundation. That integration asks a question of modern design. Why should anything be purely utilitarian? If a component must exist for strength, why can't it also add to beauty and meaning? The cathedral door answers with a whisper across the centuries. There is no divide. True craftsmanship lives in the union. The proportions of a sacred door were a calculation, a language written in geometry. In temples from India to Greece, the height and width of a doorway weren't chosen for convenience. They came from cosmic ratios, the golden section, where the whole is to the larger part as the larger part is to the smaller, a ratio you see in shells in branching trees. The builders saw this as a divine harmony. They encoded it into stone. A door built to this ratio would resonate, they believed, with the order of the universe. It was sacred geometry. But something happens when you apply such a precise ratio to a massive stone slab. It often creates a shape that's inherently stable. The distribution of mass becomes balanced. Stress flows through the structure in more harmonious paths. That perfect rectangle, born from celestial mathematics, often turned out to be an exceptionally strong one. This is where mysticism met material science, without either one knowing it. The pivot point. It wasn't just placed where it was easiest. In some designs, its position along the door's edge was calculated from the same proportional system. This could place the pivot at a point that optimized the leverage, making the door's immense weight feel lighter when pushed. The size of decorative panels on a bronze door, their arrangement, often followed these same geometric rules. What looked like pure artistry was also a grid, a reinforcement pattern. By dividing the surface according to a strict ratio, they were unconsciously creating a well-braced structure. The decorative lines often fell along natural stress lines. Modern architects and engineers look at this with a kind of awe. They see an ancient, intuitive form of parametric design, a set of governing rules, sacred ratios, that automatically generate a form. And when those rules are applied, the resulting shapes often possess inherent structural virtues. Today, parametric design uses algorithms. A computer generates a building shape based on rules about sunlight, wind load, material efficiency. The ancient builder was using a different kind of algorithm, one based on celestial harmony, geometric purity, but the outcome was similar, a design where beauty and stability emerged from the same foundational logic. This reveals the ancient world's holistic discipline. There was no separation between the mathematician, the astronomer, the priest, and the stonemason. Their knowledge was a single woven fabric. To design a temple door was to align it with the stars, to express a divine equation, and to solve the practical problem of hanging a 20-ton slab, all at once. The door felt right because it was balanced on every level, mathematically, mechanically. This sophisticated balance required a deep knowledge of the site. The angle of the sun at the equinox might determine the door's orientation, which in turn affected how it weathered storms. The local stone's properties would influence how finely the ratios could be carved. It was all connected. This integrated thinking is perhaps the most profound lesson. We live in an age of specialists. An engineer focuses on load, an architect on form, an environmental consultant on energy. The ancient master builder held all those roles in one mind. The door was their proof, a single object, a calendar, a prayer, a theorem, and a machine. A desert tomb door felt cool in the sun. That wasn't magic. It was the stone. They chose a dense rock and cut it to a specific thickness. That mass, it absorbed the heat all day, but the heat moved through it slowly. It took hours. By the time any warmth reached the inside, the sun was going down. Then at night the process flipped. The cold air outside chilled the surface while the heat still inside the stone would radiate back in. It moderated the chill. The door was a thermal battery, a passive regulator. They didn't have the equations, but they had the wisdom. Centuries of watching stone. They knew which rock stayed cool in the shadow of a quarry. They built that knowledge into the wall. Up north, the problem was the opposite. You had to keep heat in. In a Nordic longhouse, the main door wasn't just a hole in the wall. It was the start of a sequence. There was a small vestibule built outside it, a separate roof space with its own lighter door. You'd open the outer door, step into that space, close the outer door behind you. Then you'd open the inner door. That vestibule trapped a pocket of still air. It stopped the freezing wind from rushing straight into the room every time someone entered. It was a primitive airlock. They understood air was a fluid you could manage. That heat loss wasn't just about the door's wood, but about controlling the exchange of air. These weren't just tricks. It was a systems view. The door was an environmental regulator. They chose woods that swelled and shrank less with the seasons to keep a seal. They used stones with low conductivity for the desert and more insulating woods for the cold. They oriented doors away from the wind or used walls to create shelter. Every choice was about managing the relationship between the inside and the outside. Modern architects look at these practices now. They see that tomb door as a lesson in thermal mass. That principle is central now. Thick earth walls or concrete floors absorb heat by day, release it at night. It cuts the need for air conditioning. That Nordic vestibule is the direct ancestor of the airlock entries in efficient homes and labs, where you need a strict interior climate. Those ancient builders were doing design. They worked with their local environment, using geometry and material to create comfort with zero operating energy. This adaptation shows the real purpose behind those mechanical marvels. The perfect seal, the interlocking joints, the layers. They weren't just for security or grandeur. They were for environmental integrity, to preserve the stable conditions inside, keeping dry air out of a tomb, damp out of a granary, cold out of a home. The door was the guardian of a microclimate. It completes the picture. The ancient door wasn't just an object. It was an organ, a vital, adaptive part of a living structure, breathing and responding to the outside so that what was within could last. The door in its frame, balanced perfectly, it's a snapshot. It hides the journey. Getting a 20-ton slab from a mountainside to a temple threshold, that was a feat of logistics. It rivaled the door's own mechanics. Before it could pivot, it had to travel, a chain of mechanical problems, each solved with elegant simplicity. It started in the quarry. Workers cut channels around the block. Then they drove dry wooden wedges into natural fissures. They soaked the wedges. The wood swelled, a force greater than any hammer splitting the stone clean from the bedrock, a controlled fracture, using nature's own properties. Then came the move. The Egyptians didn't have the wheel for this, not for blocks this size. They used sledges, massive wooden platforms, but dragging a sledge with a stone that weighs as much as 10 cars, the friction would be impossible. Their solution was clever and labor-intensive. They poured a slurry of water and mud onto the path ahead. The mixture acted as a lubricant. It turned the sand into a slick surface, drastically reducing the drag. Teams of workers, coordinated by overseers with rhythmic calls, pulling on ropes. A slow, deliberate procession, a triumph of managed friction. For the Greeks and Romans, the technology evolved. They used rollers, placing a series of wooden logs under the sledge. As the sledge moved forward, workers behind would pick up the rollers from the back, run them to the front. A continuous track. This method transferred sliding friction into rolling friction, which is far easier to overcome. It's the same principle as moving a heavy refrigerator by tipping it onto pipes. Each roller was a temporary moving wheel. This required precise coordination. A team to pull, a team to manage the rollers, a team to guide the load. A ballet of simple machines and human rhythm. The final challenge was the lift, getting the door slab vertical, setting its pivot points into their exact sockets. For this, they likely used a compound pulley system. Like the Greek, a crane with a mast and a boom, powered by a human-powered treadmill or a windlass. Multiple ropes running through several pulley blocks, creating a massive mechanical advantage. 10 people pulling on a rope could, through this system, lift several tons. The stone itself was often prepared for this moment. Carved with protruding bosses or slots, specifically for the lifting ropes to grip. These weren't decorative, they were functional fixtures, like the lifting lugs on a modern engine block. Once the stone was hanging, suspended, the final act of precision could begin, lowering it millimeter by millimeter, using levers and wedges for micro-adjustments, until that carved pivot knob settled perfectly into its stone cup below and the top tenon slid into its socket above. Modern civil engineers look at this entire process with profound respect. They see it in pre-industrial project management, the quarrying, the transport route planning, the workforce logistics, the sequential use of levers, rollers, and pulleys. It represents a deep understanding of static and dynamic loads, of friction management, of mechanical advantage. Each step was a calculated risk, mitigated by geometry and coordination. The door's flawless operation for centuries was the direct result of this flawless installation. The static marvel we admire was born from a dynamic, large-scale mechanical symphony. It reminds us that the greatest engineering is often invisible. It's in the journey that makes the final, silent perfection possible. That flawless installation, it was tested in the end, not by people, by the earth itself. In places like Anatolia and Greece, where the ground shakes, builders knew a rigid door would fail. They saw the weakest points in a wall were the openings, the doorways, so they built those points not for rigidity but for flexibility. The lintel, the beam above the door, shows this. In seismic zones, you often don't see a single heavy stone lintel. Instead, they used a thick, long wooden beam, oak or cedar, something with give. Stone is strong, but it's brittle. It cracks under twisting force. Wood bends, it flexes. It absorbs that energy and springs back. That wooden lintel worked like a shock absorber across the doorway. It let the walls on either side sway a little, independently, without tearing the whole opening apart. The pivot points were part of this too. Sometimes the stone socket in the floor was carved a bit larger than the pivot knob it held, a few millimeters of space. That play let the door rock on its base, to shift with the moving walls instead of resisting them until it shattered. The door became semi-independent, loosely coupled. It could dance in its frame when the earth danced, and then settle back. This understanding of designing things to yield without breaking, it finds maybe its clearest expression far away in the Andes. The Inca builders at and faced constant seismic threat. Their response was in the stonework. Their famous trapezoidal doorways and windows, the sides slope inward as they rise. That shape is more stable under lateral force than a rectangle, but look closer at the lintels. Many are joggled. The stones are cut with zigzagging, interlocking teeth, like a three-dimensional puzzle. Normally, these joggles lock the lintel together, distributing weight. But during a quake, that joint has a tiny amount of give. The stones can micro-shift, sliding along those zigzag interfaces. They dissipate the seismic energy as friction. They move, they grind, they absorb the shock, and then gravity settles them back into place. The doorway survives because it was designed as a flexible joint inside a rigid wall. Modern earthquake engineers study these ancient features with respect. They see an early application of articulation, the practice of creating intentional points of movement in a structure. Today we use expansion joints in bridges and skyscrapers. We base isolate entire buildings on rubber and lead bearings so they can sway above the shaking ground. The principle is the same as that wooden lintel or the joggled stone. Don't fight the force. Manage it, channel it. Let the structure move so it doesn't break. So the ancient doorway in these regions was never just a hole. It was a carefully engineered seismic release valve, a recognition that perfection isn't about being unmovable but adaptable. The goal shifted from static strength to dynamic resilience. It asked a question: do you build for the calm day or for the storm? Their answer in wood and stone was to build for both, to create a system that stood firm in stillness but knew how to dance when the world trembled. This acceptance of movement as a fact of life leads to one last, quiet layer of the door's legacy. Not in its grand mechanics or its seismic wisdom, but in the almost invisible marks left on it by all the hands that used it. The door's pivot could act as a sentry. In some old gates, a worn bearing wasn't always a flaw. That screech of stone on stone, that high-pitched groan as the door began to turn, it was a free alarm. It announced an entrance long before the visitor was seen. Acoustic signaling. Turning a mechanical defect into a security feature. The sound was information. It traveled faster than a runner, piercing the quiet of a courtyard or a temple hall. A passive system, always on, powered just by the act of opening. But builders didn't stop with accidental noise. They engineered deliberate announcements. A simple method was to connect the door to a bell, a string or a thin leather cord tied to the inside of the door, the other end attached to a small bell hanging further inside. When the door swung open, it pulled the cord and the bell would ring. A gentle chime for a guest, a more urgent clang if the door was thrown open quickly. This transformed a physical action, the door's movement, into an auditory signal heard in another room, remote notification. The person at the door didn't have to shout, the door did it for them. In more elaborate settings, a royal palace or a high-status compound, the signaling could become visual. The pull of the door might connect, through levers and cords, to a small mechanism in a guard's post. Opening the main gate could cause a wooden figurine to pop up on a board, or a colored flag to rise into view, a primitive status board, a silent mechanical message saying, "Gate 1 is open." This let a small number of guards monitor multiple entrances from one location. They didn't need to be at every door, they just watched the board. Modern engineers studying communication history see these systems as foundational. Early examples of sensor-triggered events. The door is the sensor, its movement is the trigger. The bell or the flag is the actuator, a complete if simple automated circuit, all mechanical, no electricity, no code, just levers, strings, and gravity, a primitive but effective form of data transmission. The message was binary, open or closed. But in a world before telephones, that one bit of information was incredibly valuable. It answered a critical question: is the boundary secure or has it been breached? This approach shows a creativity born from necessity, and a deeper principle, the integration of systems. The door was no longer just a barrier or a passage, it became a node in a communication network. Its primary function was supplemented by a secondary, intelligent one. It could talk. This mechanical signaling relied entirely on physical linkages, a chain of cause and effect that had to be perfectly reliable. If the cord snapped, the system failed. It demanded precise design and durable materials. It pushed builders to think in terms of interconnected actions. That same ingenuity, linking one action to a hidden consequence, was also applied to a more secretive purpose. If a door could be made to announce itself, could it also be designed to hide something completely? To make a whole passage disappear, a hidden door has to erase itself first. In the Valley of the Kings, that erasure was total. The builders weren't fitting a door into the cliff. They were carving the door from the cliff itself. They chisel out a huge slab, leaving it attached by just a thin spine at the pivot. Then they'd cut it free, swing it open, hollow out the chamber behind, and swing it closed. When it was sealed, the door's surface was the cliff face. Every grain, every color, every fissure matched perfectly, because it was the same stone. There was no seam, no outline, no handle. To hide it even more, they'd pile loose rubble against it, stones from right around the area. The door didn't just blend in, it disappeared. The mechanical principle is perfect alignment, seamless joinery. It removes every visual cue, every tactile cue. Your eye sees a random rocky slope. Your hand feels only rough stone, nothing to grasp. Nothing that suggests a moving part. The engineering focus was on the negative space, not on the door but on the absence of a door. That required a staggering geometric precision. The slab had to be cut so that when it swung back into place, the carved rock faces met with a gap maybe as thin as a hair. Any wider and dust would gather in the crack, making a visible line over time. Any misalignment and the texture wouldn't flow across the joint. They were solving a puzzle where the only correct solution was invisibility. This art of concealment took other forms. In medieval castles, a door might be hidden behind a movable wall. A section of stone wall, balanced on a central pivot, could swing open if you pressed the right stone in the pattern. The mechanism was hidden in the wall's thickness. The pivot was a vertical timber or a metal bar set into sockets in the floor and ceiling. The weight of the wall section was carefully balanced so it would move with a push, but stay firmly closed otherwise. The locking mechanism was often just a simple wooden bar that dropped into place from inside the secret chamber. No keyhole showed on the outside, no visible hinge. The only evidence was a faint, continuous grout line in the masonry that looked exactly like all the other grout lines. It was camouflage through mimicry. The door didn't just hide, it pretended to be something ordinary and solid. Other doors hid in plain sight underfoot. A stone floor grate, seemingly fixed, might have its metal bars set into a stone frame that could lift as one piece. Counterweights below would make it manageable, or a section of wooden flooring could pivot on a central beam, becoming a trapdoor with no visible handle. The engineering focus in all these cases was the same: minimize gaps, match textures, create mechanisms that leave no external trace. The goal was to defeat not just force but observation. The first line of defense was to not be found. Modern security engineers, designers of high-end hidden compartments, they study these ancient methods as masterpieces of perceptual deception. They aren't copying the stonework, they're studying the philosophy. How do you exploit the expectations of the human eye and hand? Today, a hidden safe might be built into a false electrical outlet, a hollowed-out book behind a mirror that swings open. The principles are identical: perfect alignment, seamless joinery, texture matching. The locking mechanism is electronic now, triggered by a magnet or a biometric scan, leaving no keyhole. The ancient builder used geology and geometry to create that seamlessness. The modern designer uses precision machining and composite materials. But the puzzle is the same. Make the boundary between the hidden and the visible so perfect it becomes a secret even to the space it occupies. This ancient art required an intimate, almost poetic understanding of materials, geometry, human perception. They knew how light falls on a rough surface. They knew how a hand will skip over a smooth joint but catch on a raised edge. They knew that security isn't always about thicker bars or heavier bolts. Sometimes it's about silence, about creating a void where the mind expects solidity. The most secure door is sometimes the one you cannot see, because you cannot attack what you cannot find. This concept, security through absence, through perfect integration, it brings us to the final, quiet legacy of all these ideas. After thousands of years of innovation, from the grinding pivot to the invisible seam, what endures isn't just a list of mechanisms, it's a way of thinking. A conversation between human intention and the physical world, written in stone, wood, and bronze, Leonardo da Vinci's notebooks. They're like a bridge. You look at his sketches and you see a Roman pivot. But drawn in cross-section, a Greek counterweight system analyzed for its force. He wasn't just looking at ruins as old things, he saw them as diagrams, working diagrams. His drawings of fortress gates, of lock mechanisms, they show a mind doing something new. He took the old knowledge, the trial and error of the ancients, and he put it through the new language, the language of Renaissance science, geometry, proportion, the math of force. He wasn't copying, he was reverse engineering. He was finding the principles. This was a shift. The Renaissance rediscovered classical text, Vitruvius, Archimedes. It was like finding a missing manual. Builders suddenly had access to the theory. The ideas the original engineers might have just felt, now they could codify it. They could say this works not because it always has, but because of this ratio, this law of leverage. An ancient door stopped being just a clever trick. It became a case study in the new science of mechanics. The improvements were dramatic. An ancient lock might use gravity, wooden pins that drop. A Renaissance locksmith could add a coiled steel spring, a tiny store of energy. It could snap a bolt home, push a tumbler into place with reliable speed. Clockwork too, the gear trains from timekeeping, they found their way into locks, into automated doors for the wealthy. The complexity grew, but the core ideas, the lever, the pivot, the seal, they stayed the same. They were just expressed with new materials. With greater precision. This formalization was the link, the hands-on knowledge of the Roman engineer, the medieval mason. It was being translated into the universal language, the language of math and diagram. That created a shared foundation, a common textbook, written in Da Vinci's sketches, in the treatises that came later. These compiled principles became the bedrock of the scientific revolution. When Galileo studied materials, when Newton wrote his laws of motion. They were building on a conversation, a centuries-old conversation about force and friction and equilibrium, a conversation that had been set in stone, literally, by ancient doors. You see the legacy in the early industrial marvels, the massive lock gates on 18th century canals, their balanced leaves pivoting on giant hinges, their direct descendants of the castle portcullis and its counterweight, the complex valve gears of steam engines, controlling power with precise timing. They echo the regulated movement hero of Alexandria imagined for his temple doors. Even the ancient art of sealing, it found new life in pressure seals, in early boilers and pipes, where a failure meant catastrophe. So the thread is continuous, that's the real story. The ancient ideas weren't lost and then found, they were never lost, they were kept alive, in the craft traditions, in the masonry, in the blacksmithing. The Renaissance just provided the framework, the intellectual framework to lift that craft knowledge, to lift it into formal engineering science. The door was a constant test bed, a physical question. How do you manage force, movement, security? Every era asked it again, with new tools, new theories, but the answers always whispered back to the same fundamental truths, the ones first explored in stone and bronze. It shows you something about innovation. It's rarely a sudden break. It's usually a conversation with the past, where old solutions, once you really understand them, become the foundation for new revolutions. That final lesson from the ancient door, it echoes directly. You see it in steel and glass now. Those massive balanced stones, their true descendants are the giant sector doors in hydroelectric dams. These aren't just big gates, they're curved, counterweighted giants. Thousands of tons, they seal off entire water channels. Their movement, that slow, majestic arc, it's governed by the same physics, the same pivot as a tomb door. The immense water pressure, it's held back not by raw strength alone, it's a system. Hidden counterweights, precisely placed bearings, that's what makes the impossible weight manageable. Engineers for these marvels, they've studied the ancient systems, the pivot and balance systems. They recognized the fundamental problem, moving monumental mass. It hasn't changed in 4,000 years, only the materials, the scale. Or look at the dome of a major observatory. The entire structure, it weighs as much as a skyscraper, and it rotates smoothly, on a film of oil. The mechanism underneath is a modern thrust bearing, a technological universe away from a stone pivot, but the principle is a direct refinement. It's still about concentrating immense loads onto a minimized contact area to allow precise rotation, low-friction rotation. The ancient stonemason carving a granite socket for a bronze pivot, he was solving the same core challenge. As the engineer specifying a 30-foot diameter roller bearing for a telescope, one enabled a view of the heavens for a priest, the other for humanity. The need for a perfect seal, it follows the same lineage. The interlocking doors of a Roman granary, rebated, designed to keep grain dry for a city. They're the conceptual ancestors of the airlock on the International Space Station. In both cases, the barrier isn't just a door, it's a pressure boundary between two incompatible environments. The Roman door kept the moist outside air from the dry grain. The space station hatch keeps the lethal vacuum out from the breathable cabin. The engineering goals are identical. Create a seal so reliable the interior environment stays perfectly stable. A matter of preservation in one case, survival in the other. Modern aerospace engineers, they've analyzed ancient joinery, ancient sealing methods, not to copy them, to understand the problem-solving logic they represent. That logic creating a tortuous path, using materials that conform, it's timeless. This direct inspiration, it reveals something. Ancient solutions aren't museum pieces. They're validated design paradigms. When a contemporary architect faces a unique challenge, a bank vault door that must be massive and discreet, or a hospital isolation room door that must seal absolutely, they often start by looking at historical precedents. They're looking for proof of concept. They're asking, how did civilizations without computers solve this, without advanced metallurgy? The answers provide a foundation, tried and true principles. It proves the best applications of fundamental physics are often rediscovered, not invented. The lever, the pivot, the seal, the counterweight, these are the building blocks. Whether the material is bronze or titanium composite, the underlying conversation remains the same, with gravity, friction, and force. This continuity is a quiet testament. Our most advanced structures, they still speak the ancient language, the language of equilibrium. Written now in equations, but first whispered in stone, the door opened quietly. It didn't need a motor, it used gravity. A counterweight would fall and a lever arm would multiply that force. The pivot point had almost no friction. We think of progress as plugging things in, but these old systems worked passively. They did big things with very little effort. They used the constants of the physical world as their power source. This is more than history. For engineers working in development, this is a textbook. It's a blueprint for building things where electricity isn't reliable, where supply chains break, where resources are tight. The goal becomes resilient simplicity, not high-tech complexity. Think of a village that needs a secure granary, a door built on this ancient pivot principle, a local stone for the counterweight, a timber frame. The community could build it themselves. No imported motors, no solar panels that could fail. No circuit boards you can't fix. It uses local materials, local craftspeople understand it. And if a part wears out, you carve a new wooden pivot. You find a new stone, it's all from the surrounding landscape. The system is transparent, it's maintainable. It could last for generations. This changes how we see ancient engineering. It wasn't primitive. It was supremely adapted to its materials, adapted to its energy reality, adapted to how it could be maintained. The builders had severe constraints. Their solutions maximized longevity. They maximized autonomy. Today we face the costs of complex manufacturing. We see fragile global supply chains. These models of sustainable design feel urgent now. They ask a quiet question. Does our technology build lasting independence, or does it create a web of dependencies? A door that needs no power grid. A door you can fix with local knowledge. A door that stands for centuries. That's a different kind of sophistication. It's not measured in processing speed. It's measured in harmony. Harmony with the timeless forces of the world. That silence leaves room for questions we still can't fully answer. Even with all our study, some ancient doors keep their final secrets. The Great Pyramids. Inside there are these stone barriers, plug blocks. They aren't doors that swing open. They're massive granite slabs, each weighing many tons, slid down inclined shafts to seal passages for good. The engineering is clear up to a point. They were lowered into place. But then the final step. How were they positioned with such perfect, flush precision from the inside? The workers setting them would have been sealing their own way out. Some theories point to intricate systems, temporary wooden supports, sand-filled chambers that could be emptied from a distance, letting the blocks settle remotely. Others suggest hidden, narrow escape passages for the workers, later plugged from the outside. The exact method is still one of Egyptology's great practical puzzles. It's a climax of engineering, where that final, perfect placement was also a point of no return. Then there are the legends of fully automatic temple doors. The accounts from here of Alexandria are detailed heat hydraulics. But how often were these built at full scale? Were they common wonders or brilliant thought experiments written down by a genius? Archaeologists have found very little physical evidence of such complex hydraulic systems built into temple foundations. That gap between detailed text and missing artifact fuels debate. Was the technology more widespread than the ruins suggest? Its delicate bronze vessels and pipes looted and melted down long ago? Or were these descriptions aspirational, a blend of observed simpler mechanisms and philosophical imagination? The mystery lasts because the idea is so compelling. It lives in that space between what we know they could do and what the stories say they did. And what's still beneath our feet? In castle ruins across Europe and the Middle East, collapsed gatehouses and filled-in moats might still hide the physical truth of their counterweight chambers. Excavation is slow, expensive, delicate. A wooden counterweight box, even a lead weight, could have rotted or been salvaged centuries ago. But the empty space, the channels for ropes, the pivot stones, those clues remain. Some may lie undisturbed, holding the complete blueprint of a defensive system we've only partly reconstructed from drawings and fragments. Every time archaeologists carefully clear a new section of a fortress wall, they're testing our modern hypotheses against the physical record. These unanswered questions aren't failures. They're the engine of a living field, experimental archaeology. Historians partner with engineers and traditional craftspeople. They take a mystery, like sealing a pyramid plug block, and build a full-scale replica using only period-appropriate tools and materials. They test each theory. How many workers does it take to move a 3-ton granite slab on a wooden sledge? Does a sand release mechanism work reliably, or does it jam? These experiments are physical conversations with the past. They often yield surprising results, showing that methods we considered primitive were actually highly sophisticated, efficient. A mystery solved in a quarry field today rewrites a chapter in the engineering textbook of antiquity. This ongoing search highlights a deep humility. For all our advanced tools and theories, the ancient engineers sometimes achieved results whose precise methods we can only guess. They left behind the magnificent effect, the door that still pivots, the tomb that stayed sealed, but sometimes obscured the cause. That preserved an essential element of wonder. It reminds us that innovation isn't just about the solution you leave behind, but about the depth of understanding you cultivated to reach it. These lingering puzzles ensure the study of ancient technology is never closed. They draw in minds from archaeology, physics, materials science, and craftsmanship in a shared pursuit of one timeless goal: to listen to what the stones are still trying to say. Ancient doors, those questions that stay with you, they can't be answered by one person. You need a conversation, a dialogue between the shovel and the supercomputer. That's the final principle, the one that makes the rest of it work today: interdisciplinary study. The door is where archaeology meets mechanical engineering, and that meeting creates something new. An archaeologist gets to a site. They find a huge stone door in a fallen gatehouse. Their training asks cultural questions: who built this and when? What was it for ceremony or defense? They dig the soil around it carefully, reading the layers. They take samples: the wood, the metal fittings, the mortar. They document everything with photos and drawings, preserving the context. That's the story of the door as a cultural object. Then the mechanical engineer shows up. They have different questions. How did this thing actually work? They measure the dimensions, the stone's weight, the angle of the pivot sockets. They calculate the friction between the bronze pivot and the granite socket. They run digital simulations, modeling the forces on the lintel if the door was slammed shut. They analyze the leverage, the stress points, the efficiency of a counterweight system. That's the story of the door as a machine. Told separately, these stories are incomplete. The archaeologist might admire the symbolic carvings, but miss the genius of the load distribution. The engineer could solve the physics puzzle, but not understand why such an overbuilt mechanism was needed for what looks like a minor entrance. But when they sit down together, with the same measurements and the same artifact, that's when it happens. The engineer's stress calculation explains why the door was reinforced in one specific spot, and the archaeologist sees that spot bears a clan symbol. which suggests that family's role was to defend that exact weak point. Or the archaeologist's dating of a repair layer in the threshold shows the engineer precisely when a wear compensation system was added. So you get a timeline of incremental innovation. Materials scientists join this too. They put a fragment of a bronze hinge under an electron microscope. They don't just see an old piece of metal, they see the crystalline structure of the alloy. They can identify the ratios of copper to tin and trace elements like lead or arsenic. That tells a story about supply chains, about metallurgical knowledge. Maybe the analysis shows the bronze was deliberately work-hardened right at the pivot point. A sophisticated understanding of material properties to reduce wear. That technical insight gives real weight to the historical text that calls the city's smiths master artisans. This collaborative model is now a blueprint. It's how we study ancient ships, siege engines, aqueducts. A historian's translation of a papyrus manual is given physical form by an engineer's replica. A materials analyst finds a unique Roman concrete recipe, and a chemist explains it through reactions. Each discipline has a piece of the puzzle, and the final picture is always richer, more accurate, more human than any one expert could have drawn alone. This approach changes the ancient door. It stops being just an artifact in a museum case. It becomes a vibrant data point, a single point in a vast, interconnected equation of human ingenuity. That equation has variables, culture, religion, politics on one side, and constants, physics, material science, geometry on the other. The door is the equal sign where they meet. It's the physical proof of a civilization applying its deepest values, security, reverence, permanence, through a masterful manipulation of the physical world. The enrichment goes both ways. The engineer gains a deep respect for pre-industrial optimization, for solutions born from intimate observation, not abstract formula. The archaeologist gains a new lens, seeing technological capability as a direct expression of a society's priorities, its intelligence. Together they learn something. The story of human progress isn't a straight line from primitive to advanced. It's a spiral, where fundamental truths about balance, force, and material are discovered, then forgotten, and rediscovered in new forms across the ages. Studied this way, the ancient door is no longer a relic, it's a teacher. Its lessons aren't written in one language but in many, and they wait for a whole chorus of voices to read them aloud. The word primitive starts to feel not quite right. It suggests something lacking, something crude, a step towards something better. But a door that works perfectly for 1,000 years. That seals a tomb in the desert for, that balances tons of stone on a point of bronze. That isn't a crude first try. It's a peak of optimization for its specific time, its materials, its purpose. These weren't prototypes. They were the finished product, the masterful result of a long conversation. A conversation between human minds and the unyielding laws of physics. A conversation that went on for generations. Each door is centuries of quiet, cumulative experiment, watching how wood swells in the rain, how bronze wears against granite, how a pivot placed just so makes a massive weight feel light. This was deep, observational science, not recorded in equations but in perfected practice. Technology born from intimacy with the natural world, not from abstraction from it. And that forces a shift in how we see progress. We tend to imagine a straight line, climbing steadily from simple to complex, from weak to powerful. But the story of these doors suggests a different shape. A spiral maybe, or a tree with many branches. A civilization can reach a state of supreme, elegant efficiency within its own context. The ancient Egyptian stonemason who perfected the pivot socket wasn't waiting for the ball bearing to be invented. He had solved his problem so completely that for his purpose, the ball bearing offered no real improvement. His solution was, for his world, the final word. That challenges our modern bias. The bias that newer is inherently better. That complexity is a mark of advancement. Sometimes the most advanced solution is the simplest one that works perfectly for a lifetime, or for 100 lifetimes. So viewing these engineers as our peers, not our predecessors, changes everything. It's an act of intellectual humility. We aren't standing on the shoulders of giants who saw dimly. We're standing beside them, looking at the same eternal problems, friction, gravity, force, security, but with a different toolkit. They had an intuitive mastery of material behavior we're only now relearning with advanced microscopes. They understood passive energy systems we now try to emulate for sustainability. They achieved a durability we often struggle to replicate with our more complex assemblies. Recognizing this parity isn't to diminish our own achievements. It's to properly honor theirs. It frames their work not as a beginning, but as a parallel expression of human ingenuity. And this perspective quietly critiques our own technological hubris. In an age of planned obsolescence of disposable gadgets, a door built to last 1,000 years is a radical statement. It speaks of a value system where longevity was paramount, harmony with local resources. Their simple tools, the lever, the wedge, the inclined plane, were wielded with such profound understanding they created monuments to permanence. Our powerful tools can sometimes create fragile systems. Systems dependent on global supply chains, on constant energy input. The ancient model asks a question we are only now, urgently learning to ask again. Does our technology build resilience or does it create dependency? The door that needs no electricity, that can be repaired with a piece of wood from the forest, holds a different kind of sophistication, one measured in endurance, in autonomy. In the end, this redefinition invites a deeper respect for the cumulative intelligence of the past. It wasn't the flash of a single genius that created the perfect temple door. It was the slow, collective wisdom of countless unnamed masons, smiths, carpenters. Each generation refined the design, fixed a flaw, observed a failure, passed on a slightly better understanding. This knowledge was embedded in the craft itself, in the feel of the chisel, the temper of the metal, the angle of the cut. It was a living library, written in muscle memory and tradition. When we study these doors, we aren't just analyzing old mechanics, we're decoding a legacy of solved problems, learning from master practitioners who, with simple tools, achieved a kind of perfection we still struggle to define. Their work stands as a quiet reminder. True advancement isn't always about what you add. It's about how deeply you understand what you already have, an Egyptian tomb door pivoting silently. A medieval castle gate balanced with a hidden counterweight. These aren't just old things, they're a kind of hidden lesson. A long, slow class in engineering history written in stone, in bronze. For thousands of years, these objects have taught the same things: the elegant power of leverage, the deep intelligence of balance, a close, almost poetic understanding of materials, and a complete vision, what we'd now call systems thinking. These lessons aren't locked away, they're still useful. They whisper answers to engineers now. They show that lasting innovation usually isn't about complex parts. It's about the elegant, insightful use of basic physics. It's a reminder. Before computers modeled stress, there was intuition. Intuition from centuries of watching stone. Before synthetic polymers, there was an artisan's knowledge, knowing how wood swells, how bronze wears. That deep, gathered wisdom is a kind of intelligence. We're still learning how to value it. So as we finish, here's an invitation. Next time your hand reaches out, next time you push open a door, just pause for a second, feel the weight and the motion. Listen for the quiet mechanics. You're not just going into a room, you're interacting with a technology refined over thousands of years. You're touching the end of an old conversation, a conversation between human ingenuity and the fixed laws of the physical world. It's a legacy of quiet genius. Built into the frame of